Hello everybody, welcome to another stream. How are we doing? So, last stream we got the two shaders up and running. Although one of them is a bit slow, a bit too slow. So this one um, constructs the initial tree of the volume of spheres, and then the other one, the other shader we got up and running builds this thing called an occupation map where there's like a 3D texture. Wait, sorry, this one here. Yeah, it builds a 3D texture where each bit represents a cluster of spheres which is filled up with spheres. So if I give it a quick run, we should be able to see that the first shader that we got up and running takes really long. Takes 32 milliseconds. And this is because I'm trying something a bit different with it. And there appears to be a bug, or yeah, I'm pretty sure it's a bug because no way is it's taking 32 milliseconds. But yeah, in the queuing system, so effectively, like to save. So in the previous version of this, we used to spawn one of these per level of detail, and what used to happen is you'd spawn you do one dispatch, and this works on L0. Then when that's done, the next one will work on L1, right? But how it works on it is it literally spawns a single thread. Okay, there's a thread group per cluster, so each thread gets a sphere within that volume, and then runs over all of the edits and sees if they brush over that single space. And then if it does, we put a sphere there. So the reason why we moved away from this one is because it will be running over a lot of empty space, and that's not good. So I moved to a different approach where I was like, okay, we'll just have one invocation, and we'll start on L0, right? The first cluster, there's only one cluster on L0, and it's a 4x4x4 now. And then when it's finished, it will push all of the children that have had sort of edits that have brushed over that space will be pushed onto the queue, and then there'll be other sort of computer units running, and they'll simply take them off the queue and start doing the same thing on them, and that will recurse down all the way until we reach the highest level of detail, which is cool and everything, but this is what the queue code looks like to take something from the queue successfully across multiple threads, and there's a bug in it, and yeah, it's a bit of a bugger to track down. So still haven't solved the problem, but my feeling is that so we've launched like I don't know, like 500 compute units or something like this, and they just keep running until they all have finished basically. And until they're all in this loop here where they can't seem to get any more work, and they just terminate. And this seems to be hitting here when we do this print statement, but also it seems to hit here where we've sort of spanned for too long or something, and they just terminate. So I have a feeling that basically I have a feeling that this is taking 30 milliseconds because some of them are getting trapped in here or something like that, and they only end because of this. But I'm not entirely sure that's true. Anywho, I'm thinking that this code is a bit too complicated anyway, and it's probably best if we actually improve the solution rather than trying to fix it. And I've came up with a solution. So it actually merges this solution and the previous attempt that we've done. So this previous attempt used to launch this shader, as I said, right? It does all of the classes in L0, and it goes over all of them. Each thread gets a sphere in L0, and the next one goes over all of the spheres in L1. Hey there, Arbit random user. Sorry. Yeah, Arbit random user. Welcome. How's it going? So what I think we need to do with this new approach is do a very similar thing to where we launch one per LOD, but improve the fact that essentially you probably use the queue system still to get the next cluster. So we're skipping the empty space, because the problem with the old solution is it would have a thread per sphere, and if that sphere hasn't been touched by an edit at all, it's going over all of the edits and working and seeing if it's been hit or not, and it just doesn't get hit. So it ends up ultimately being a waste. So what we're going to do then is just get rid of all this code, all this queue code, and just replace it with like indexing into a queue basically, or probably a ring buffer now. So let's go ahead and get that sorted out. I think we want to change this to a probably call it a ring buffer now, because that's what it will be. So we're still going to do like a for loop here. Over all of the level of details. So I think we want to do something like LOD 0 data LOD count, and in order to get this to work, we're going to have to use dispatch indirect, and the previous one is going to have to fill in the direct arguments on GPU, or the indirect args on GPU. So that means all of this silly nonsense can go as well. And I'm hoping to be able to get rid of that completely. So what this is this algorithm works by just spawning the maximum number of compute units on a GPU, and you can't really get that number very well. So it's basically you have to kind of guess it for each piece of hardware, which is not a good idea, because there's a lot of hardware out there. But yeah, so I'm glad we're improving that bit. So the buffer that it comes from is in the globals. Let's find another indirect that's done it. Here you go. So we use the global buffer, and inside the global buffer there's going to be one called, what's this one? Tree construct dispatch args. And then we're going to index it with LOD, and then take the address here. Wait. No, yeah, that's right. So in this sort of globals data structure, we've got to add these dispatch indirect arguments. So we need 10 of, I think it's 8 of them now, the number of LODs. Or it's 7. So we've got those in there. So we just have to populate them now. So that needs to be called a ring buffer now, this one. Ring So a great thing about this ring buffer is now it doesn't have to be mem set to E32 max, which is great. Make sure I get this right. Okay, so I don't have to do this anymore and mem set it. And in the volume constructor reset, we have to now set it up in here. So when we initialize the volume constructor before we end up constructing a volume, we put onto the ring buffer, the root node. And we say, it's got one in there. There's a head and tail index. Do we need a head and tail anymore? Because you just need to be able to insert. Yeah, so you probably just need what's known as like an insert index or something. No, you probably need a head tail so you can know, so you can calculate how many to launch the next. All right. So when you ring buffer, excellent. So when you launch, yeah, so we insert the insert index after there now. Yeah, so this ring buffer now, it can actually be a smaller size. So this was allocating the maximum number of nodes. But all we need is the maximum number of nodes on the highest level. And probably round it up to the nearest power of 2. Yeah, so I probably want that in the shared as a constant, so we can do some nice tricks, I think. So the maximum number of nodes on the highest LOD is, well, nodes is 64, right? Because this times 4 is 256. That's the most number of spheres. So 64 cluster nodes. So it's that cubed. That's 256k. So 256k. That's the most number of clusters. And that is a power of 2. There's only one bit set. So volume constructor ring buffer size, and then we'll do that number there. Must be a power of 2. So if it must be power 2, maybe I should do some of this instead, right? One shift left. What is that? 18? Yeah. So you want to say this is 64 to the power 3, aka number of clusters at highest LOD. Must be a power of 2. Excellent. So now we've got some good qualities for the ring buffer, so we can cheaply index into it now as well. And I have to worry about when we overflow the integer. So reset the volume constructor, get the insert index of the ring buffer. Oh, that's not good there, is it? Ring buffer insert index. Okay, maybe we can shorten that name in the future, but for now that'll do. So now that we're launching this many times, okay, so now we're launching this shader, one for every LOD. Oh wait, I didn't fill in the dispatch args, did I? Where are these dispatch arguments? These ones. So really we should fill these in. We'll just stick in a for loop. Is that in, oh, it's just in there, right? For, she moves into core shared, so I can get in my GPU code. Alright, there we go. Wait a minute, that's a viewpointer though. Then a viewpointer on GPU. If HCC else, we'll just assume it's going to be a U32 on GPU. That way I can just be lazy about running for loops. Alright, so LOD, you shouldn't really be using it. There's any, yeah. Maybe this could be shared across many threads. Maybe I can just say LOD count, right? And then you probably want to say, move this to the beginning. Put all of this in a conditional block and just say if sv dispatch index dot x equals 0. So it's the first thread. In this case, this example, that will be true because only one group is launched. Actually, no, it will be across the whole of them as well. But yeah. So this is in the global. So we're going to access it with this lovely macro. And we're going to use the dispatch index dot x. So, you know, there'll be 7 of those, and we can then initialize x, or this to one, probably 0, 1, 1. Yeah, so we'll be upping the x coordinate in the shaders. In the big shader, which is going to get kicked off. So this one though still needs to actually set this to 1 for the root node. Set .x to 1 for the root node. So now the first LOD 0, is going to have dispatch args with 1, 1, 1. So that means this shader down here will be launched once, and it does one cluster. Right, and inside the cluster it's a 4x4x4. Okay, so now what changes is we no longer have this big old loop anymore around the outside because we're not doing multiple clusters. These are a lot more short-lived invocations. So we no longer have so now we have a ring buffer, but we need to get our ring buffer so we kind of need to know, like, where, like, the offset we need to apply to our dispatch index. So maybe we need a head and tail still. No. Yeah, so next to these dispatch args, we need a place to say, hey, this is where the nodes the start index is. How will we know that? It's as if we need to launch like another shader in between, which could just say, where was that index, and then sort of we'll have like a start index or something, I guess. We'll just call it that. So we probably need to launch another shader. So after reset, we need another sort of 1 by cluster tree construct setup or something, I don't know. We probably don't need any constants. So here, we simply just need to look at that sort of global insert index. Oh, wait a minute. Alright. Head, tail. If it's not traditional sort of, I guess we'll call it a read index as well. I don't know. Tail, head. So I don't care about the read index here. So you'll read from the head index and store that in the read index. Are you doing this full time? No. Welcome there, worship. Worship the surfer. Welcome, welcome. This is just on the side, so I just do this sort of like after work, like 3 days a week. Sundays, Tuesdays, and Thursdays. If you're interested in the timetable, it's on Twitch, so you'll be able to see it in your time zone. But yeah, so I work on this on the side, basically. So yeah, so read the head index and store it in the read index. So the next time this shader gets called, it can use the read index. Oh yeah, but the head index has to be moved up to where the tail is. Let's read the tail in as well. And then in the head we store the tail. Okay, so this shader has to be launched sort of next to the it has to be launched next to this guy. So you have to do a standard dispatch on this shader. So this one does a read write to global data. And then what goes in here? The number of groups, right? Let's launch the one. E32 times 3. 111. No constants. Right, awesome. So that'll launch before, just to set up this guy so it has the variables set correctly. Because if we did it in a previous invocation, it's difficult to know what is the last thread in this shader that finishes. Like, it's just impossible to know that. So you have to launch one of these guys just to say like, oh, okay, it's all finished now, and we'll sync code here to stop it from, because they both sync on this. So then it can sort out those global variables. Okay. So now we can read from the queue. So where's the old read from queue stuff? Here. Damn it. So there's no longer needing for atomics. because the caches would have been flushed with the CPU barriers because there's whole separate dispatches in between here. So it's called the ring buffer now, and there's a read index, which is again this thing here. So it's read index plus. I'm not sure I like that name now. But anyway, maybe I should call it read base index, and that might be a bit better. So from the read base index, we're adding SV dispatch index X. So, is that right? No, dispatch group index. Right, so we've got each group is a 4x4x4, but all of our groups, we have this many groups along the x-axis. We only have one along the y and z, right? So there's just multiple x-axes here. And this is controlled by the dispatch indirect args here, which is set up, so they're all set to 0, 1, 1. And there's 7 of them. And we're launching 7 of the shader below. 1 for each level of detail. So L0 is going to have just 1 in the X that we set here, right, for L0. That's because it just has the root node. There's only one cluster node there. So there's a 4x4x4 set of spheres in L0. So there's only one cluster in L0, and it's a 4x4x4. So we need to somehow set this for the next level of detail, or we need to keep adding them every time we add something to the ring buffer, basically. Now, something to keep note is this is not correct because it's a ring buffer. This is going to overflow. So what we need to do is do the lovely and there's a constant somewhere. I call it size as well. I don't know the word size. The word size to me means size in bytes. So I typically just use the word count instead. So because this is a power of 2, because this is a power of 2, this is the number, right? It's power of 2 because only one bit is on. This means that if you take away 1, you've got all of the bits that comes on before it, which means if you want to do some sort of wrapping, if you have an addition which overflows the buffer, right? So you'd end up overflowing it, but you want it to wrap back around. You can basically AND it with a power of 2 take 1, and that'll wrap it around. So it only keeps these bits. So that's how we avoid the overflow there. That's super nice. So now this means we can get rid of all of this code here now, which will be super awesome. Let's delete the variables we don't want. So this horrible Q code that was written, horrible thread safe code can just be nuked, which is super great. I think we need to set up LDS still. So LDS, we still need a children bit set. Hey there, Wajilla, how you doing? How's it going? It's been a while. How you been? So if we say, hey, am I the first thread? And it's like, yes, I am. What can you do in Atomic? Store into the LDS memory. Now we're using LDS because on the GPU we're running in wave 32 mode, so there's 32 threads running in lockstep. But inside a thread group we've got 4x4x4. There's 2 compute units running independently in lockstep. So later on down the shader, we need one of them is working out the children bits, other one's working out the children bit set, and we need to sort of get them to communicate with each other which ones, or to like basically share the bit set across the threads. So we use the LDS memory to communicate that. So that's super nice. We need to set that up. The first thread does that. Set up LDS. Means local data storage. Right. So radio. We should put barrier in there as well. So all of this code can just get deleted, which is amazing. No more complicated queuing system anymore. It's just kind of a simple index, and you get your cluster index out, and that way it's in tune to just how compute shaders typically work. You have an index and use that, and off you go. So we probably want to have a safe check here. Do you want to have a safe check? Maybe not. That should be fine. TM. Doing good. Still working on CAD stuff. Got Vulkan up and going there. Awesome. Well done. Good stuff. That's an achievement. Congratulations, sir. Yeah, things take time, but you got this. Have you got any sort of pictures at all? Any images? And also, what sort of CAD software are you thinking of making? Like, is it to replace something like Google SketchUp or something like that? Or is it, you got some different ideas? Got a cube rendering sorter. Nice. Oh yeah. So this all stays the same. Well, we go over all the we have a cluster. Each thread has a sphere. Goes over all the edits. Does the collision detection with the sphere and the ellipse or axis line bounding box. Check if it's gonna add or remove that sphere. Keep track whether or not we need a child or something like that as well. And then after we've done all the iterations over all the edits, we have we combine all of the has-sphere booleans and the alloc children nodes into bit sets, and then we store the bit sets into the node. And then we all the children bit set into the LDS memory. I don't know why it needs to be an LDS. Maybe because I load it back out again. Yeah, and then I use that to see whether or not I need to dispatch more children. Right, so they get pushed onto the queue here. Very domain specifics for jets and jet engines. Oh, nice. Taking inspiration from SolidWorks for parametrics. Have you got a link to that so I can see it? Or the thing you're referencing? Because I've not heard of it actually. So this is where the old code we pushed onto the cube, and now it's a ring buffer. So we get the ring buffer, and we've got a new thing. Have we still got tail now? I think I called it. Yeah, we called it tail still. So we'll do an add. Now we've got our insert index. So what we need to do is we need to do the we need to do that lovely and where's the bugger? This one. This take one. Right, again, just to do the wrapping. Yeah. To do the lovely wrapping, wrap. This will overflow the ring buffer, so wrap it round. And then insert the child cluster index in there. Sweet. Cluster sphere index. Right, this is one for the refine pass, but we haven't done that yet. We'll re-look at that after. Right, so I think we're there now. Let's hit compile and see how much we buggered it up. Alright. So let's just double check and make sure it's all good, because I don't want to like fire this thing up and it just destroys the stream. So let's just double check it. So this is what launching from CPU side. We've got this our constants for this shader here, the complicated one, and we set up all the resources in there and the data. We've got this shader which basically sets up the level of detail. It just copies some parameters over, which we'll look into that in just a minute. And then is that synchronized on the global buffer? That's correct. And this synchronizes on all those guys and then launches this based on the indirect. We didn't finish that. Yes. So one thing we also need to do is we need to, as well as atomic adding there, we also need to add. I was thinking, so we could add to this atomically, or we could just we could also just find out. That could add some time to the shader. So we could just do it once in this shader here, which is called at the beginning. So this should be equal to tail take head. And I guess you can't have this do nothing. So you have to say max of 1 as well. You technically can't have that do nothing. And you have to put the LOD in here. I don't know the LOD. I could maybe... I could store it as a global, or I could have it passed in. I might have it passed in with some constants, maybe. It's the better thing to do. Awesome, take a look at that link. Thank you very much. Oh. So they have like a product which is, right, some CAD software, basically. Yeah, I guess I don't really care about showing videos about this software. Alright, but fair play, I didn't think about this stuff existing. Makes sense though. They definitely look like they're inspired by Adobe. This feels very Adobe-esque to me. Um, what did I call it again? Pre-construct setup. Right, U32 LOD. That's all I want. That's all I wanted. Alright, so from C. Oh, BC LOD. You're setting up that LOD. Yep. Actually, so maybe we don't have to set it in there. That's... Okay, so let's just architect this a bit better. Sorry, I can do the extra work every frame, I'm not fussed about that one. Okay, so bc.lod equal LOD. So now this will have the LOD passed up in that shader. Excellent. So now we're setting up this every frame. So let's double check the shader. So at the end of the thing, at the end of the after this has finished and it goes around to the next one, right? I'm going to call this guy the setup LOD shader. So it's going to get a head index which is set by the previous call to this, by the previous version of this. So at the end of here, see, we set it to the tail. So by default, we set to 0 in the reset. But then, like, we're going to add stuff in the construct shader. We're going to add more entries to the queue. And simply, yeah, the head is going to set to the tail after this invocation. So if we do tail take head, that will give us the number of nodes that we, so let's just call it like clusters to process count. And that's this one here. So we set up that LOD, and that launches that many clusters. Then, and then the read base index for this one is going to be head index, and then the new head will be tail. So when it comes into this one now, it uses the read index, base index, and the group X to get its cluster out and start going on that one. Excellent. So I think that's good. One thing is though is to handle when how do I know that this was equal to 0? How do I know? So these both go into here, which means we can get that same information. So if the read base index and the head index are equal to the same thing, then that means that there's actually nothing to do. So you might as well just quit. Well, you have to quit, because if not, that'll be an invalid index. It'll just be garbage data. So what you're going to say is if read base index is equal to that, then we say we want to say like there was no clusters to process. There is no clusters to process. Kabam. Do you have any gameplay right now? No. We're working on the renderer. We have a lot of like engine foundations in. We have like a UI system. We have multiple controllers support, multiple keyboard support. Like it's all running on Windows and Linux. We also have yeah, what else do we have? We have some bits. We have a GPU system, a graphics system, and yeah, some operating system abstraction. That's about it right now. But working on a kind of unique renderer right now. All right, so I think I'm happy to actually go and launch this now and see how well it goes. Yeah. So fingers crossed that is better than what it was before. Alright, so what I'm going to do is I'm going to do a sync. So if the stream crashes, because AMD drivers suck apparently, if your shader runs for too long, like you get an infinite loop, it will close your system. So I'll be right back if that's the case, but it shouldn't do, right? So here we go. Alright, we're still here. So what's great is that's actually an improvement. Yes. That's an improvement because it was 32 milliseconds. Now, is it an improvement over what we had before? I don't think it is. Yeah, so the previous implementation, we just did one invocation of the shader. It was taking 32 milliseconds, probably because there was a bug in the dodgy queue reading code, but we've just basically nuked that and redesigned it. So now this is how long it's taking with a single edit operation. Now it's taking 0.5 milliseconds for a single edit to go across all those spheres. Now I'm trying to think, is it actually better than the previous code? Right, the last one's taking 3 milliseconds. Excellent. So it turns out that we've probably got a... This is the old code. So the old one used to launch this shader. So there's two major differences. This one was doing 2 by 2 by 2 clusters. So those clusters had 8 spheres in them, right? 2 by 2 by 2 spheres in there. And then, so obviously L0 is one cluster, and it each had a 2 by 2 set of children and went down. until you got to L7, which is 256, or L6. Yeah, L6 or something, which is 256. So the way the approach used to work is it used to go over every single sphere within that 3D volume, even if it got filled up or not, right? The way the new system works is it still does one dispatch per level of detail, but it uses a queue instead, or like a ring buffer instead. So on the first level of detail, we go over all of the edit operations, and if they only cover the right hand side of the volume, well, only the right hand side children will be put onto the queue to then get processed, and the same thing happens again, right? And that'll build a higher level of detail, and it'll repeat until they've all all the level details have been touched. So this just means that we won't be going over all of the edit operations for clusters that just haven't had edits brush over them. So it's a massive speed increase there. So we end up... See, this thing is going to be slow. It is just going to be a slow shader. We want it to be as fast as possible. This is only with one edit operation, so we're spawning a single sphere in the middle of the volume, and that's getting filled with spheres in there. So that's only, yeah, so that's just one volume. We have thousands, maybe like 1,000 volumes. We'll take time to do them, but we can do them in the background or something, right? So okay, this is good. So what we can do now is we can bring back this code, and this sets up the occupation map. So we'll visualize what actually went on. Let's just double check quick. All right, it's using the refined process queue. That's still fine. We can use that. Yeah. So this builds an occupation map, so we can like simplify this structure and also build different level of detail. We can build the lower level of detail information from the higher level of detail information. Let's just build, keep the music going. Right, so now it's running here. We haven't got a visualization in game because that is effort. So we just use render doc, which is a great tool for doing this stuff. So we launch a render doc, it does a frame capture, first frame, and we'll be able to read in, so we're able to look at that texture. So we got this working last stream. So if you see last stream, you'll remember. Here it is. Okay, so each pixel is a bit set of 32 bits. And each bit is a cluster. So it kind of does like a 4x4x2, right? So yeah, each bit is a cluster of spheres. So if we go, as we said, we spawned one edit operation of a sphere in the middle of the 256 cubed volume. So this is us visualizing all of the clusters which are completely full of spheres, but maybe not completely full, but mostly full. So I think it's 56 spheres in a cluster. This is the visualization basically that we're seeing. So we know it's working, which is great. But as you can see, we've only got one MIP. If we go to the other MIPs, it just doesn't show anything. And this is because we need to run the next shader, which is the downsampler. So our custom downsampler, I kind of already had this one working in the previous iteration. So it's just a case of just making sure it works. So it's just a custom downsampler. Here it is. Yeah, so this is just a custom downsampler where it works at the bit level and with repeated information, because there's repeated information within the bit set, so we can reduce the amount of samples we need to do when we need to use this data structure in the next stage in the refined pass. Yeah, I'm not going to go over too much how this thing works, because I've mentioned it like many times. All right. So, all right, this should run. Okay, so we've got 4 downsamples that have gone off. I think that's right. So we run it in RenderDoc. We should see a downsampled version now. So we've got the first frame capture. We're going to go into here. Right, here we go. So this is the highest MIP. Let's go down to the lower MIP. See nothing. No. Right, so it must be working with the old. No, it can't be. It's working at the cluster level. Something's not right. Something is fishy. Let's go to MIP 1. I don't feel like there's any. So going to the middle, there should be something here. The middle slice in the middle of the slice as well. I cannot see anything. Any number, right, shown up there. So it's completely empty, which is not good. So let's actually just get in and read the code. Let's see what's going on. So we're launching. This is how we're launching it. How many MIPS has it got? Right, this is for the old number of clusters. There are 128 cubed clusters. No. 64 cube. Wait. So 1 less LOD for those. Alright, I need to rewrite that comment because it doesn't make too much sense. Well, I can't figure out exactly what it means. So clusters are 63 cubed and it's a bit set, right? So 63 cubed. Why does that matter? So it's XYZ. It's a 3D texture, right? It's a 3D texture. You got 64 cubed resolution at the highest LOD. So, but the first one is 33, isn't that right? Yeah, because it clusters in, which is 64. Uh, 64 divided by 2 plus 1. The reason why it's divided by 2 is because we're using a 2 by 2 by 2 bit set. within that 4x4x2 yeah, what's the best way to describe it? So the way the system works is you've got, for a single texel, there's a 4x4x2 bit set, right? And the top left 2x2x2 is unique. The rest of them are repeated and come from the ones, this comes from the right, this comes from right and down, this comes from the down one. And they all take this one from the neighboring ones, right, and put them in here. So it allows us to do some nice, it allows us to check. If it's to look at this cluster here, we can tell if it's completely surrounded by other clusters. So it's pretty neat. If we're just 2 samples, we can do all that. From all three axes. So we've got 2x2x2 bit set that's unique. Yeah, so it's 32 plus 1, so it's 33. That's the size of the texture. So you're going from 33 down to so you're just like half in 33 basically until you reach 1. Does it do like a round up though? I think it does. So did I actually get it right? That's the question. It goes down to 2x2x2, so it's not right. So we just did take 1. Yeah, so I think that's the first problem. Is that was kind of like off by 1. But that's not, that doesn't sort of say why it's not rendering anything. So we set up all the texture views so we can do some storing in the shaders. Because unfortunately in shader programming you don't have a way to store at a MIP level. You can load from any MIP level, but storing at a specific one, they don't have that for some reason. You have to have a texture view which has the first MIP as the MIP you want to target. So that just creates those, and that's fine. Oh, I think I see a bit of a problem. Oh, the base one is there. Yeah, that's a good idea. Okay, so we're setting the destination to base plus 1, source to base. Yep. Yeah, I'm not sure if it's divided by 2. Is that right? Oh, it is this truncating one. Okay, that's fine. Okay, I think that's fine. The dispatching looks fine. This is the shader that does all the work. So what we're going to do is we're going to comment this line out, and we'll just put a new one in, and we'll just set all the bits to 1. And we should be able to see white basically, and if that, and that'll just tell us. Yeah. That'll tell us if it's actually storing, and that's something we can work with for now. There's a 1 by 1 by 1 there, okay? So I'm seeing a red. So I'm seeing no red on MIP 1, no red on MIP 2, MIP 3, but on the 1 by 1 there's a red. And then here obviously there's red where it counts. So that's weird. So have I bugged it? Why have I bugged it up? Why is how's it working out the coordinate? That's probably an out of bounds coordinate, I reckon. Oh, the group index. Interesting. How's he getting that? Dim. The dim will be. Dim will be. What is dim? Well, yeah, it'd be 33 initially, wouldn't it? Um. So it'd be 16 when it's divided by 2. Yeah, I don't see any problem with that. That's pretty straightforward. So I wonder how. Like, we look at the console output. It's literally launching at 1, 2, 3, 4, 5. So if you see here, you've got the first one downsample 0 to 1, then 1 to 2, 2 to 3. Yes, there's enough, right? That's correct. Um, yeah, I think I remember actually we discussed that there was probably a bug in render doc, right? But I couldn't be bothered to. Should we get a new version of render doc? Because I remember I'm using like a really weird version. Because basically I haven't been bothered to update it. Um, let's take a look at the it's an extra now apparently. Let's get that one. Can I force it? Should I go to that layer then? Or can I tell it to force? Yeah, it's been installed there manually in the past, I think. Oh, you can identify which file owns that. Interesting. Maybe you've already got one installed. Random dot capture. No package owns it. Should probably copy pasted that path, but I think I did it right. Nope. Alright, let's just delete it. Right, good old sudo, let's get in there. Then let's remove that from the history, you know. I don't accidentally go up and press it. Alright, they're all good. So yeah, we're gonna still run it up, the new version. And we're in. So let's take this new one for a spin and see if that one helps us. So let's remove that thing, compile it, render doc. Oh, proper version. Rightio. So we check the output. There's the 1x1x1. There's the first MIP0. Still not seeing anything. Not good. Let's try it again with the orbits on. We might be able to see what's being passed into the push constants as well, maybe. Okay, so MIP5, which is 1 pixel, has all the bits on. You should be seeing all the bits on here, but you're not. Same here, you're not. So should we take a look at the pipeline state? Compute shader. Here's the destination value 4140. So the one before, yeah, they're one less. That's correct. So I'm curious. Has 6 MIPS. The view covers 1 MIP. The view covers 2 MIPS. The view covers 2 MIPS. MIP count 6. How do we get back? Check this one out. Yeah, base, MIP level 2 and 1. That's what I want. Hey, 9-to-5 office worker. Do you have a job? And if so, can you hire me? No. I'm sorry. I have a job, but I work for other people. And I work for a big company, so it's a big formal process. And I don't think there's any open jobs in it at the moment. Hey, Soulphone. How you doing? How you been? Do you have a job? Yes. Yes, I do. 9 till 5:30. I'm not 9 till 5 guy. Soulphone, no. 9. I'm uber confused. Uber confused. I have a vague memory that there's a bug in RenderDoc that didn't show the image. So what we're going to do is we're going to load from it and see and print out the pixel or something, you know. So we'll print out two things. So I'm going to print out, hey, this is the coordinate. And then there's the pixel. DST bit set coordinate and then P. Rightio. See how much that works. I see all the pixels on. See, I think this is the bug we encountered before and it didn't show up in RenderDoc for some reason, and I don't know why. It's bloody annoying. So basically we know it probably works. Like, put it this way. Let's put bit set in there now instead. If we see some bits on, then we know it works. Yeah, see, so some of them have got some bits that are on, yeah? And this means that it's sampling from the one before it, right? So we see, and then it's putting it into the destination, then it's reading it back out. And these all seem pretty sensible numbers to me. They're not massive coordinates, right? They're all like pretty small. So yeah. Alright. So it works. It's just not showing up in RenderDoc for some reason, and I don't know why. I'm after the correct time and everything. Right, so let's put the proper one in, back in. And will I rerun it for RenderDoc one more time, just double check it. Hey Glorious Sir, what's going on? We're just cracking away at the volume constructor, and yeah, we've made good progress. We've got the volume construct leaf node shader working. I had to split it up into separate invocations again, but it's got probably a 7 times increase in performance, or a decrease, whatever way you're gonna say it. I don't even know anymore. But yeah, it's 7 times faster. So it used to be like 3.8 ms plus all the previous ones here, and now it's 0.5 ms plus all the other ones up here. So it's probably about 7 times better. So that's really good. We're just getting the downsample one up and running now again. and I think we have. But yeah, we're about to start the tree refinement pass. Yeah, I've been good, man. I've been good. Just been I took a month off streaming because I was at work, obviously, because I was on holiday. But I'm back now, going full ham again. Hey there, Downsy, how's it going? Oh, office worker, what's up, man? What's up, man? Are you okay? Um, so let's move on to the next shader then. Oh yeah, I wanted to see this running, didn't I? Is it something that I just didn't miss? Bro, the amount of weed I smoked this is super high. Get it? That's cool. I'm not sure how much you're understanding right now, because thinking on weed isn't easy. Um, so there's nothing here that sort of rings any bells about MIP levels not getting the appropriate data shown in the thing. Maybe I'll press it again. I'll do a second capture. There we go. Ought to be good enough. Hey there, Cat Pain, how's it going? I think that person was probably about 14. Maybe. Right, so let's view the image. I don't expect MIP, the one by one MIP, to see anything. What? So I'm not seeing anything on the one which is a bigger, the later frame. It's not showing up anything. But on the first frame it shows up that, but not anything on MIP 1 or MIP 2. But it definitely writes to it though. I'm super confused. Should we go see why that is? Because like render doc, MIP level incorrect. Bargain view non-power 2, that was in 2016. I doubt that's still a problem. Yeah, I don't know why it's doing that. I don't know why. Like, it's definitely writing data to it. Let's just confirm that one more time. So we know the number. Yeah, let's just say if this is equal to 41 or something. Because I think 41. Yeah, let's print out some of these guys, but only if they're like one of the final MIP levels or something. I don't know. I'm not sure if 41 is the final one, but we'll keep upping it and just looking at the printed data, and the numbers will just get less and less. Right, so only printed one entry, that is the last one. And I expect it to be 0 because that is saying that, hey, the whole volume has to be completely filled, kinda. Oh, yeah, well, yeah, the whole volume has to be completely filled, that's alright. So we move down to 40. Oh, bugger. Yeah, we move down to 40. We might start seeing some. Yeah, okay, so we're seeing some with data, yeah. But the interesting thing is they're different every. Oh, they're not different every frame. They're just displayed in a different order, and that makes sense. So 0, 1, 1 is still the same number, yeah? Alright, so that means we know it is deterministic, right? The same input gets the same output, at least. Right, 0, 1. Sorry, 1, 0, 1. Same number. And this is like the low resolution MIP, which means it's gone through a few layers already and read and combined or whatever, right? Downsampled. So yeah, that's fine. Man, it's so bloody annoying. I don't know why this doesn't work. Is it because it's just too much data already? Is it because it's copied too much data this frame already? I don't know. Anyway, so the downsample works. That's good. So now on to this refine LOD. Bum, 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 bum. How does a refine LOD work? So it works the opposite way around. It works from the bottom of the tree and goes up. So the previous ones started from L0, and sort of tried to construct this one, see if you painted over at these higher level of details, and if you did. Sorry. If you painted over any of the area, any of the children, and if you painted over any of the children, it will queue up the next load of children, and then it will dispatch over L1 and do all of the children which had been sort of visited in the previous dispatch. So instead, we've got all of the clusters, all of the leaf clusters. So a leaf cluster is a cluster that has no children, right? But it doesn't necessarily mean it's the highest level of detail. You can have this cluster which had been drawn in, and so we put a sphere down there for it. But it didn't have any children because you explicitly painted at that level of detail. So yeah, we've got to be careful about that. So we've got them all in some form of queue, but we want to be able to. Yeah, I think we want to do a similar system, a similar rework. So I think we want to do something where we have a ring buffer, but what we do. Yeah. Yeah. So I need to refactor it to be to be a ring buffer instead of a queue. So it's going to work on all of the clusters in the queue that were put in from the first time. and then it's going to append more on the end while it's working on these guys. It's going to find out there's the parents of those and put them on here or something like that. Wait, how does it do it again? Let me double check that. Oh, it ends up storing some of the data in the tree, so it finds out if it's the last child to do it. Okay. Yeah, so it goes over all of these leaf nodes. If it's the last child of a parent to be processed, it's gonna put the parent node in the queue, and then all of the, I mean, it will basically stop here because that's where like the end of the initial workload was, and then it's gonna run another shader which sets up the dispatch arguments to say, hey, there's another 6 of them or something like that. And then fires off another dispatch, and you'll have everything all set up again a second time around. And it works on those guys and adds more to the queue and then repeats, right? And it's a ring buffer so it can wrap back around and overwrite old data. So we need to adjust everything to work the same as that. So it's no longer a process queue, it's a ring buffer. And that's going to be as big as the highest level of detail. How does make system work? That goes from the... Yeah, we'll get back to that one. Oh, I call it ring buffer. So we no longer have to clear it because we know exactly which one we're looking at. So in the constructs we need to pass in the ring buffer here. So when we construct the initial leaf nodes, we're going to add the leaf nodes that we find into this refine ring buffer. So just need to sort this out. This is now a process ring buffer. And this is ring buffer. So when we dispatch this now, we're going to have to launch one of these per level of detail. So we need to do the same thing here again. And I think we need a setup shader as well. Right, but how do I want to work with this one? Yeah. So this would be called like refine setup LOD. Could probably use the same constants there. Hmm. So we'll launch this shader. You know, 6 times. But it needs to be using dispatch indirect, a bit like this one. But we need to be using, what is it? Actually, it's like this one here. So in the global buffer, we're gonna have the dispatch args, and we're gonna populate them in the setup compute shader, which runs just before. And this will take a look at the queue and see how much we added the previous time to the queue, and then we just say, hey, we're launching that many instances of that shader. So get this right. Why is this read write? Can this be read only? Yeah, it's read only. On that texture. Okay, so we need to add these refine arguments. So in the globals buffer, we're going to add construct. So we're going to place that with refine. So there's one of these for each level of detail. And we should probably stick a comment here saying we are not launching for each level of detail here. We are not launching explicitly for each of detail here, since the construct leaf nodes shader will populate the ring buffer with there you go. So populate the ring buffer with all leaf nodes, and these can be on any level of detail. Right. We're not launching explicitly for each level of detail, but for the number of LODs. Since the shader will populate ring buffer with all the leaf nodes. These can be on any LOD, but this doesn't matter. Alright. So that's great. We're going to make this shader now. Very easy shader to make though, because it's just a copy paste from the one we made the previous time. So we literally just copy this here and just give it a rename. Let's go past all of the occupation map stuff. Right. We're going to put the word refine in here now. And yeah, we just got to put the word refine where it says construct, basically. And we're going to make those guys in the global buffer. So there's a read base index, and that is used in the refine shader to know for all of the stuff that have been launched for this level of detail, where's the base read index in the ring buffer for me to read from. You got a head and a tail index from a ring in the ring buffer, right? So this one literally just sort of like gets the head and tail, works out how many clusters that need to be processed the next time around. Why is that saying root node? That's not correct. All right. Then it stores that in the dispatch argument. So this is saying launch this many of this shader. It's got a local size of 4x4x4, which is one cluster. There's all the spheres in a cluster. So we got the read base index, and that'll be the old head index, right? So say we insert 6 elements, right? That's going to increase the tail index, but the head index will stay at 0. And so this will be 6. We have 6 guys to go. 6 gets put into here. So launch this 6 times. That's 6 clusters to process. The read base index would be 0, right? So when we read from the ring buffer, we start at 0. And then the head index will then be put to 6, right? So that means the next time, the next sort of, when we go around the whole way again and land back on the shader for the next LOD, this will now be 6 instead, right? And then that'll be whatever 6 plus the number that we inserted that time around. So now the beauty of this is we get to remove all that ugly Q code. So I'm just going to go and grab the ring buffer code. All right, so that's all the code we need now instead of that horrible Q code that we added. So we did some sort of like thread safe Q thing. Not a good idea. And this system replaces that. And it means that we can still only process the clusters that need to be processed rather than every single cluster for a level of detail. So that's super powerful. So we just essentially like merged the two approaches that I had. So remove this while loop now. Wait, there needs to be an if check somewhere. Give me a sec. Oh no, that sets up the... Have we got LDS memory? Oh, I don't need LDS memory anymore. Ka-ching. Ka-ching. So, yeah, we get rid of this Q code, this horrible thread safe Q code. No longer needed. Okay. So I'm just going to format this code correctly, and then we'll refactor the insert code as well, and then we'll double check this. So basically we've got a process ring buffer now. And this uses the, not the word construct, the word refine instead. So we get the read base index and the head index. We, if they're equal to the same thing, then this means that there is no clusters to process, right? Whoops. I copied and pasted that from somewhere, so check that. Okay. Here it is. I wrote back. So we read from the process ring buffer with a read base index plus the dispatch group index, because the group index represents a cluster offset. Because we're launching this many, well, this is how many threads in a group, and each group is a cluster, so there you go. So we get this offset into the ring buffer, and because it can overflow the ring buffer, we want to wrap it back around, so we use this trick. That's the power of 2, take away 1 from a power of 2. That gives you all bits on. So that's the power of 2 number. Take away 1, that puts all bits on. If you AND it, it gets rid of all of the other bits that come after and just wraps it back around into a number which is less than this one. So we can index safely into this ring buffer and pull out the correct node. So now this, so the way this shader works is it checks to see if the node has any children. If it has any children, it's going to see if there's a wait, kind of 2x2 spheres? No. Right. In a 2x2x2 set of spheres in the children node, it's going to see if 7 or more of them are set. And if it is, then that's a single it's a single lower level of detail sphere in this cluster. So essentially, if we just draw this so it makes more sense, here's a 4x4, and this is a slice of 4x4. There's actually 4 of them going off into the Z. So there's a 2x2. So for each of these guys, right, there's a 2x2x2. Okay, so first of all, this cluster is split into a 2x2x2 set of clusters, and that in the higher level of detail. So there's like an octree of children. So that means there's actually a 4x4x4 of spheres that go into each of these clusters, right? So as you can tell, this bigger sphere, this lower level of detail sphere, has a 2x2x2 that go over it. So if 7 out of 8 of those are there, then this guy needs to exist. So this is how we add. So this is how we, if you've painted down at higher level of detail, but so we haven't made the lower level sphere yet. This is the code that does that. So after that, we basically see whether or not we need to keep. I don't think that's correct. Give me a second. We fixed that in a previous one, I think. Yeah, let me correct that. Boom. All right. Yeah. So all right, what am I doing? Yeah. So what does this code do here? So let's at the child cluster, and yeah, if the child cluster, yes, if the child cluster has a full set, mostly full set of spheres, this is 56 out of 64 or more, Then this is where he uses that occupation map and does a very sort of smart two sample thing and some bit shifting magic to basically check to see if the child cluster is completely surrounded by other clusters. If it is, it just gets rid of the higher resolution cluster because we've got a lower resolution one and we'll use that one instead. So that just means that on the inside you'll get bigger spheres, but not within a cluster. That was a bad drawing example, but the basic idea is when you have a guy like this, you'll have little spheres, right, like that. But then, like after a certain, technically it's after 4, then you'll start getting like the bigger spheres, right? That are twice the size. So it just allows us to like process less spheres overall, basically. We'll have less spheres in memory. So we try and have spheres by the surface, kind of. Well, there's 64, right, in a cluster, so we'll see how useful it is. Maybe it's not that useful. We can always remove it later. Yeah, and then that's basically it. It does that. Wait, what does it do? Yeah, it does that if it has any children. Um, and then if we're the first thread within the cluster, we see if we have a. If we don't have any children, then this node no longer has any children. So subtract the total number of nodes. Interesting. Did we mutated that, right? Yeah, good. So subtract the total number of nodes. So when we sort of copy it from the build space into a persistent place in memory, we can have the exact number we need to allocate, basically. So you still need to do a GPU allocator, which would be fun. This piece of code here is basically just saying if we don't, or if we have a parent, check to see if we're the final child, and it adds it to the process queue. Now this is the stuff we've got to change because it's actually a ring buffer now. So we're going to go back up and find the insert index code for the other one. Alright, so this is the other shader. Let's say ring buffer. It's fine. This would be ring buffer tail. So I need to wrap it here because that should be set back to 0. Alright, I've got that rename there. Right, so what am I looking at? I'm grabbing this, aren't I? Yeah. So right, here's the code. So we want to still use the refine tail. So we're going to atomically add to that. It doesn't matter if it overflows because we get the index. If it overflows, it's completely safe because this is a power of 2. The size of the ring buffer is a power of 2. So we can take the insert index and and it with this special number as well. So it's 1 less than a power of 2, and that will wrap it within the ring buffer if it ever overflows. So we're going to put in there the parent node index, and that won't get launched until the next iteration. So I think we can try and launch this shader now. Let's see how this goes. So let's get it compiling. Sure. Did we set up right? Yeah, 0, 0, 0. Good. Does that need to be an atomic load? Probably not. Just a load. So it doesn't have to be an atomic because it comes from a separate dispatch, and the pipeline barrier will do the cache flushing. So you don't need any atomics in the shader, for that case at least. I need the word ring buffer in it. There we go. Right, that's everything compiling. So we got it ready to launch as well. So hopefully this works. Yeah, one more double check. I want to just see the yeah, that all looks fine. Did we set those up? I'm not sure we set these up. So if you go into the volume constructor reset, we actually do this, right? We need to say, hey, for all of those dispatch args for each of those level of details, put x to 0 and the rest to 1. And then we will be basically setting the x value later on. So we set the x values here, right? So in this setup shader, which is called before the refine one, it will work out the number of clusters we need to process. All right, so let's see if this works. So we should be seeing, well, yeah, it shouldn't be freezing, basically, that's the plan. I'm glad this is working much better now. So, yeah, if the stream crashes, I'll be right back. But it's just the AMD driver just falling over. Okay, so we're running. Excellent. So the refinement is running. And it looks believable. Because the first one is going to be the most expensive. And it is, right? So the first one has all the leaf nodes, and and then you go up to the parents. So the more you go up and up and up, the quicker it should get. So I guess, although I don't really know how well it went, because these ones, like the next LOD and after that, all have about the same. Which leads me to believe... Oh, that one's got bumped up a bit. Maybe, I don't know. Yeah, they're all kind of about the same, in the same ballpark. Yeah, they're actually all in the same ballpark. Which leads me to believe, like... yeah, it's probably just a very small number that gets processed, actually. So there's an easy way to tell this. And we just literally print out here in the setup one with the LOD number. It's not really LOD, it's kind of like, we should really call it iteration. So if I say something like iteration this. And we want to say like has of this. So we just put in BC LOD and then that one there. Bam. So we should, well, I need a new line. So you should be able to see, like, did it work past the first one, right? And the answer is no. So for some reason, no parents are getting added on. So this means that basically a lot of the code is just not even being tested. All of this code here, which is the meat and potatoes of it all, like this whole if statement and down, is actually not getting tested. So the only bit that's kind of running, all right. So it turns out we need more. We need to test this one. So there's something weird. All right. So how it knows if it's the last one to insert or to reach the parent basically is it uses inside the parent node cluster. It uses the children bit set and uses the higher bits. So the first like 8 bits. Yes, the first 8 bits here represent is a bit set to say which children exist. And the next 8 bits say which ones have visited the parent and said, hey, I've been refined. And the last one to do it, it could be any one of them, the last one to do it is the one that then puts it on the queue, basically. So that's all this code is doing. And I can get back to it. That's all this code is actually doing here. So I want to print out this sort of children index. Just to sort of see what's going on. And if we should be seeing a number from 0 to 7. And if we're seeing something different, then it's concerning. But so that's all I'm looking for initially. They all are like 0 to 7 to me, I don't see anything else. That's good. So what's the next sort of thing which could be the problemo? So we're doing an atomic bit OR on here. We've got the bit ready, right? So it's this times 2. That times 2 is not good. It's actually that plus cluster children count. Right? Or it's cluster children count plus that. Probably a bit more understandable. So it's 8 cluster children count. So it's 8 plus index, and that's the amount we need to shift it over. And that's our sort of visit bit, if you will. Or, yeah, that's the bit. So you put the bit in there, and then you shift those 8 bits down, get the low bits, and if they're equal with the last one, be there. Okay, so that is it. That's going to open up the floodgates, and yeah, we could possibly end up crashing the stream, so hopefully not. Right, let's go. Okay, we're still running. And we're processing actual nodes now. So you can tell this is correct because the last one processes 1, which is the root node, right? Which means that Oh, and this one processes 8. So because you have at least one highest level of detail node, it's got to go all the way, yeah, because you've got one highest level of detail node. Ah, that's scary. So this is our highest level of detail node. This one, when it is done, it can let the one above know that it can be processed the next. Sorry. Because you got one of the highest level of detail nodes. Yeah. This parent one cannot go until this one is finished. Right, so because you have one in the highest level of detail, it takes obviously the number of level of details to actually get back up to the parent, right, in a way. I'm not really explaining that the best way. But anyway, basically just because it's at the bottom, the highest level of detail, it's going to take every iteration to get that chain of nodes through. So it just makes sense there'd be a 1 there, and there's 8 there. So that means that on L2, when you've got 2 by 2 by 2 set of child nodes, those are all apparently being processed on that second to last iteration. Right, so we at least know that it is running correctly. We still don't know if a lower LOD sphere is being placed. So we still don't know that. Hey, sis, welcome. How's it going? How you been? So I guess we can just sort of scream created lower LOD sphere, and we'll just watch that sort of just beam out into the terminal. So I could do more of a better check though, right? Right, we don't see that scream out into the terminal. Which means there's no lower LOD spheres being created. So why is that? Obviously this checking code is a bit wrong. Doing alright, just finished work for the day, cool. How's everything going? Yeah, it's going good. We're nearly done. We've made good progress today. Sort of refactored a couple of the shaders, and comparing it to the first attempt of the LOD system that we did, and it turns out this first set of shaders is like 7 times faster from the changes we've made, which is great. I haven't checked the down sample. I don't expect that. No, yeah, that's gonna be quicker because there's less data. We're just doing the refine now. But yeah, it's going well because there's only one more shader after that, and that's the make persistent, where it copies it from the local build space where you've just got like the biggest allocation you've just built in that area, and then it will essentially take all the ones where you're like, oh, these ones I want to keep, and then it puts them in the persistent space. So I still got that one to do. But yeah, we're going to write. I'm just making sure that this is functioning in some manner. But But yeah, it's going good. So I'm hoping soon. Yeah, I'm hoping to be done by next stream, all of this stuff. And then maybe Sunday stream we can get it plugged into the ray tracer that I've already written. And kabam. I'm still confused. Why no? Maybe create a lower sphere, and we'll put the count in there. Like, how many does it count? I think this is just off. So it only has one in there at all, or zero. One or zero. Great. So let's put in one of these and just see what happens. One of these bit sets. All of the bits are on. What about if we do this and this? Alright, so now we're going to do another one with another number afterwards. Put like a pipe in there or whatever, I don't know. Why did I do that? Anyway, and the other number afterwards is going to be the result of that. Is bit counted. So maybe does my bit count code in the compiler not work? Oh, we're getting stuff. We should print it as hexadecimal then. Well, no, maybe not. Yeah, let's create it as hex. Three. The 3 is 2 bits each, right? So we've got 4 times 2, and that's 8. So bit count is working. Oh, so when I add... Oh my days, it's a boolean. So obviously that converts this non-boolean thing into... Okay. So it's great, my boolean coder works in the compiler. It converts a non-integer... Sorry, it converts an integer into binary number, right? 0, 1. So, yay. Okay, so we are creating... I don't know why that just bugged out, but we are creating lower LOD spheres. So, good. That's good. Hiya, how's it going? Hey. Wow, 30 months. Been a long time. How you been? How's it going in Canada? Longest marriage ever. Hey, it's not... This, okay, marriage? Where were these vows? Yeah, I hope things have been going well with you. Weather was treating us nice for a bit, and then it went crap. Yeah. Yeah, I'm hoping we get that nice spell of weather you had. Because right now it's like pretty bad here too. Because it's my birthday soon. And I'm doing a barbecue. And I want the barbecue to be outside. But yeah, we'll see. How's the old KU going? Yeah, it's going alright. It's nice and cold. It's starting to get light again. Starting gradually. But yeah, it's good. Just been working mostly, and yeah, but the trip was good. Lots of exploring and like spending time with my wife and my son. So it was a lot of fun. Well, yeah, the clocks are going back at the end of the month, I think. We don't do it. We do it 2 weeks later than the US. So, and I guess Canada does the same as the US, right? So I think George Bush, whatever, changed it to be different from the UK for some reason. Yeah, if I remember my history. Yeah, last weekend, right? Yeah, so ours will be 2 weeks later, maybe. Oh no, maybe it's 31st. I have no idea. I just find out through someone else. When it's ever to do with like normal news or anything, someone else just tells me, and I'm like, okay. I never keep track of these things. Um, See, I think the refined thing is, oh yeah, I want to do one more print statement, just to be like, oh yeah, works. So this code deleted it, mate. So this will just say that we end up deleting this cluster because we've got some. It's surrounded by other clusters. Yeah. So yeah, we're deleting clusters, which is fine. That's cool. I'm happy about that. What about subtracted it, mate? So this is when we have completely deleted all of its children. So this should happen as well. Subtracted it, mate. There we go. So this means this refined shader is probably working okay. Like, it's definitely working okay enough. Excellent. Right, so we've got one more shader to get working. And that's the make persistent shader. And this just copies it. Wait, I made this thing? Oh, yeah. So this just copies. So you've got your sort of like cluster tree in GPU memory somewhere. And it's sort of like. Let's use this one. You got your cluster tree in GPU memory somewhere. Each one of these is a cluster. But you've said, oh, I want to keep that one. I want to keep that one. Well, you're not saying what. Sorry. We're going to go down the tree and work out which ones we want to keep and which ones we don't. And the ones that we want to keep, we actually just copy over to a new place in memory. We also have a number which represents the number of nodes that we want. And in the setup shader, we're going to do a custom allocator at some point, which allocates in this more persistent space. Say this one uses this much memory. The persistent space might use this much memory, just a bit smaller. And so you've got 3 nodes in there or whatever, and it just copies them in. Right. I don't think it works exactly like this, because all children have to be linear. So 8 children sit next to each other, but this is the basic idea. This will be smaller than this, unless you've completely filled up the volume. So yeah, let's get these plugged in. I've got to remove the silly queue. I think it works the same. Oh, we work from the root node and go down. So it works the same as the first shader. All right. So we're going to do a similar thing. There's a make persistent setup. Why do we need that? That sets up the volume. I might turn this into the no, but this one does the custom allocator. Yeah, okay. Right. So what we're going to do is make persistent. We're going to make another ring buffer again. Ring buffers all the way. Oh, did I not put ring? I didn't put ring buffer size in the allocation. So all these ring buffers. I need to shorten some of these names, they're just far too long, but one day. We'll clean up the code when we've got it working. So yeah, ring buffer. Yeah, good. Alright. Oh, it's the wrong bloody one. There we go. Alright, so we no longer need to mem set it. This can all go. Yeah, that clear one needs to still happen on the occupation map. And we make persistent, we need to put the ring buffer in here. And we're going to need to do that same for loop again, where so this one is going to go from the root node down to all the children nodes, and just see if they need to be kept and copy them over. So that'd be super nice. So rather than calling it refine, I'll call it make persistent. Persistent. Oh, wait. Spell it. And again, it's a process ring buffer. Right, I'm happy with that, I think. Oh, and we've obviously got to add the dispatch indirect stuff as well. Because each of these, when we launch them, we don't know how many groups we're going to launch. Because we're going to launch just enough every iteration. So again, instead of refine, put the word in, or words make persistent. Cool. So let's go to that globals buffer and get everything set up, and then we'll go and edit the shader code, and then hopefully we get this thing all set up. So this is all going to be like ring buffer, head index, and all that. We need to read base index, so each invocation, each separate dispatch, iteration of the dispatches will get a different read index. So for every different LOD, basically, we get a different base read index in the ring buffer. Then we need the dispatch args as well. Make persistent. Excellent. So we need to set all of this up. Right. So it's in. What is it in? Yeah, volume constructor reset this one. So we need to set up the dispatch args to be 011. Is that still right? Does that make persistent shader? Yeah, there's one cluster at a time. Yes. You're launching over clusters, that's good. So the X will get upped in the shader code, and that'll be like, for every cluster we add one. Or we put one into there basically. Which is super nice. Alright. So that's all that information set up. The next thing is to go to the make persistent stuff. Wait a minute, I need the I need this. And I need to make persistent version one of these shaders that is called. So this is called, the setup LOD is called before every time this is called. Every time before that is called. So we've got to place the word construct here with make persistent. It's the same pattern as the last two shaders. We're going to take the head and tail index. The tail tells us the tail will be so many in front of the head, and how many in front it is, that's how many clusters were added the previous call to this make persistent, right? And that's the saying, hey, we've got this many clusters to copy over in the next iteration. So then we obviously add, that's the dispatch args for that LOD, and that controls how many times this thing gets dispatched the next time around. The read base index would be the old head index. That could be 0, for instance, and then the new head index will be the tail. And there we go. So that's super nice. We've got to change a few things. Right, so we are going to set this up here. Right, so a custom allocator thing, set that up, that's all fine. It sets up the volume in the persistent memory. We can reset that back up. Then we add to the process ring buffer the root node. Then we simply do what again? Right, copy the root node over and store in the location in the source nodes where the new node is, so we can patch it later. Right, okay. Make persistent, that's fine. Okay, so now we can remove that horrible Q code. So we basically copied and pasted everywhere, because I didn't bother to try and improve it until today. So all this horrible loopy Q code, which I thought could be okay, but it turns out wasn't. So rather than the word refine here, we're going to use the word make persistent because we need to use those variables instead. Oh. Right, so now we can go over this shader and just double check everything is the way it should be because it's actually a very small shader, which is great. So we get the read base index, and if it's the same as the head, it means there's no clusters added, so we should just return. Because compute shaders have to launch at least one. So you just launch the one and get it to end. Now we do read base index plus dispatch group index, since each group of 8 by 1 by 1 is a cluster. We only need 8 threads, unfortunately, so it's not going to be the best, fastest shader. But it's just it's what we had to do. It's okay because it's the only one that does it. So we essentially do like a wrapping add, right? We add and then we wrap it round and back into the ring buffer. Put out the cluster index, read the cluster, and then we pull out. Hey, it's the same language. Okay, right. So pull out where the node was written to, right in the destination buffer. So it was stored back into node. Right. When it was initially copied. So that's really great. So if we have any children, we work out the start index. Yeah, we bump allocate the nodes. What the crap is going on here? Right, it's fine. Yeah, so we bump allocate the nodes, the 8 children, on one thread, and then the rest of the threads read from that thread, and then add the child index, which is 0 to 7 inclusively, so it'll be different on each thread. And then this will be, yeah, then it gets the source index as the destination source index, copies over child, and then clears the extra bits that were put in there during the refine pass, and patches the parent index to be where it was stored in the new buffer. And then, does it do anything else with it? Yeah. And then we store where the child was copied to. Yes, then we store it back in here. We store like the version for the version of this, which is pulled out of here, but for the child node instead, where that was stored into the destination buffer, and then push each child onto the process queue. Now we have to do that same code as before, where we do the wrapping insert. So it's a process ring buffer, and we're going to use the make persistent tail index. We're pushing on the source cluster index. I'll update some of these comments actually. I'll get back to that in just a minute. Right, then if it doesn't have any children, if you're the first thread, you're going to patch the children cluster nodes to not exist. Excellent. Yes, that's actually that looks pretty good to me. It's pretty straightforward. So let's quickly process that at a time, takes from ring buffer and evaluates the list that it's over the cluster, then we push. Yeah, something like that. Right, so shall we try and get that shader up and running then? I don't think we need this anymore, which is good. Because I didn't want an algorithm depending on knowing the number of compute units in a piece of hardware. So I'm glad we got rid of that as well. Okay, so does that work? Oh, so reading from source cluster nodes. Correct, isn't it? So do we have the tree make persistent? Oh, I spelled that wrong. Persistent. Cool. Right. So fingers crossed this is going to work. And then we can just test out to make sure it works, and that'll be the whole volume constructor finished. And then in the next stream we can actually move on to just trying to get the thing to render. So yeah, the stream crashes, I'll be right back, but it shouldn't do. Okay, that's good. So here's this make persistent shader being called now 7 times, something like that. I don't know. So the first one's going to be instant because that one is the root node. Now they should get more expensive as time goes on. Yes. Okay, so that looks believable to me. What's going on there? Obviously can't tell without interpreting the data in some way. So is there a way that we can quickly put some prints in here to sort of see like, oh yeah, that's fine, you know? Like we go without saying. Mm, yeah, it should be alright. So this means then we should have a cluster, well not a cluster, a volume. A 256 volume, which has spheres which cover this center space like this, right? So a sphere which is filled with spheres, basically, right? Because because we've got one paint operation, which is a sphere that got placed down, and that is going to be filled with spheres. After all that, all those shaders, all these shaders here, they all ran. They all took about 1.7 ms. Yeah, I don't know how. Hmm. Yeah, I think we've got the benchmarking on as well, so it doesn't. Wait. No, it wouldn't have any overlap anyway. Yes, this is only with one edit operation as well, so I wonder how bad it gets when you have quite a few. Yeah, so we've got to figure out intelligent ways on how do we sort of like insert this into some frames so we don't get, um, how many volumes. Um, yeah, the volumes that we make and ship with the game, they have to make sure they're not so complex that you can't maybe build one while the game's sort of running. Or maybe we don't, maybe we build them when you sort of boot up the game and just store them in GPU memory. I don't know. Entirely depends on what the game looks like at the end of it. So this means now that we have a volume in GPU memory. So we need to build another shader which traverses down the tree in a similar way to how we've done here, and checks to see if the volume should be rendered. Sorry, the cluster should be rendered. And so do like occlusion culling, and see if it's in the frustum and stuff like that. And then if it should be rendered, we throw it into the screen tiles. Or we throw it onto a list of clusters to render, and then you run another stage which does the tile binning and then renders it. So what I think I might do is I think I'm going to commit this code now because it's been a lot of work since I've actually last committed, and it's just better if I just get this all up on checked in now. Yeah. Right. So we want to commit. I don't know what my last one was actually. Update plan for LOD cluster 2. Okay, so we just want to basically say, complete LOD clusters v2, but nothing has been rendered yet. Right, so I get that pushed up to the GitHub for those who are following and have access to the code. If you'd like to get access to the code, you can follow the link there, and you can follow the instructions and see how you can get access to that one. Yeah, so next stream we'll do another shader which sort of like renders it as we'll try and render this cluster basically and see how that goes. And yeah, from then on out, we should always have stuff rendering on the screen, basically. Should be super cool. And from here on out, just be improving what is being rendered on the screen. Be sweet. Right, let's find someone to raid because I've got to get going. So our next be on Thursday at 6:30. Oh, what happened there? What is this? Yeah, Nico's on. Oh, you can actually watch them now. Excellent. Imagine if... hopefully you didn't get ads in here. Right, let's give Nico a raid. Rightio. Thanks for coming, everyone. I'll see you all in a future stream. And yeah, have a good tomorrow and Thursday. I'll see you all on Thursday. Right. Bye.